Okay, ladies, sorry, got halfway through the first problem before I remember to hit the record button. So stop and copy the first problem, and then you can pick back up here. All right, so we took the set an inside equal to u, took the derivative and rearranged it so it said what dx is. So now we're going to do a bunch of substitution. Look here, you're going to say the antiderivative. You're going to take out this, and in its place you're going to put u. So u squared. There are a couple of ways you can do this next part. I'm going to show you the way that always works, and sometimes you'll see a shortcut after we go through the problems, okay? Then I'm going to take out the dx here, and I'm going to replace it with this. And for the problems you're going to see, anything that's still there that has an x in it should cancel, okay? Anything that still has an x in it should cancel. All right, so what happens is this 2x cancels with this 2x, and I end up with the problem, the antiderivative of u squared du. I have basically changed the variable. Okay, and I know how to take this antiderivative. This is just power rule. So u cubed, right? 1/3 plus c. And then I need to go back and resubstitute the original function in there that I did at the very beginning. What was u equal to at the beginning? Square plus 1. And that's all there is to it. Okay? It's not particularly difficult. There are a handful that are a little harder than this, but most of them are.
And the reason it's keeping a C on it is because it's not
Not a definite interval, correct. The indefinite interval also called antiderivative. All right? Let's do a second one. Sometimes you'll see it, you'll see what you need to substitute, and then you'll skip some steps. And I'm going to encourage people right now just to keep all the steps there. Sometimes some funny things happen. All right? You want to pick the internal function. What's being raised to a power? Let it be your other variable. It can be u, you can call it z, it doesn't matter what you call it. Okay? Take the derivative. Usually just go ahead and write it this way. That everybody can sort of skip that step instead of saying du dx and then multiplying by dx. Just go ahead and put the dx on the other side. All right, and some people like to write this next step, and some people don't care about it. I'm going to go ahead and write it because every once in a while, if I don't write it, I mess up. But sometimes people can stop right here and do what they need to do. Okay, then you're going to go up here and substitute. And ideally, what's going to happen is anything that's not taken care of by the u is going to get canceled out by whatever showed up in the du, in the dx. Does that make sense? So the 6x's cancel out. This doesn't always happen, but that's our ideal. And we have a change of variable. So the antiderivative of u cubed is 1/4 u to the 4th plus c. 4 is in u's in the same problem. And go back and substitute the original function in, and you're done. Okay, next one's going to have a little twist in it. It's almost the same function, it doesn't have a 6 there. Again, we let u equal that internal function. We take the derivative of both sides. This is the same thing we got on the last problem. The difference is that there's a 6 floating down here in our derivative, and there's no 6 up in the interval, in the definite interval. Yeah.
Will the outside thing always be equal to the derivative of the inside?
No.
No.
When it does, like on the first two, you can usually skip the steps. When it does not, this is when you want to make sure you have it before. Okay? All right, so when I solve this for dx, I get du over 6x. All right? And when I go to do my substitution here, this time everything doesn't cancel away. Y'all see? What does cancel? As long as the variables cancel, then you're gonna be all right. If there's just an extra constant floating around, that's not a problem. Constant multipliers are not a problem. So my x's cancel, but that 6 does not. That's a constant, so I'm gonna pull it out to the outside, and now I have almost the same problem. It has a constant multiplier on it. So what will be asked, just make sure y'all all heard what she was asking, is the derivative of the inside always gonna be what's sitting there?
And then it's the not yes.
It is a u, thank you. All right, in the first two problems, I made them up so that the derivative of the inside, this part, was sitting right there. Okay, that's the way the first problem was, and the derivative of the inside was sitting right there. But that's not always the case. However, when it doesn't sit there, if there's nothing left but a constant multiplier, the problem is not difficult. It's still easy. So this is 1/6 times 1/4, u to the 4th. So this is 1/24, 3x squared minus 2 to the 4th plus. Okay? All right, we have about 5 or 6 things that we might do for substitution. So this is the first one, option number 1. You have the integral of f of x to a power. Try letting u equal that function that's raised to a power. It will not always work. It is one of the things to try. Okay? And sometimes there's stuff out and about around it, a 2x on the outside or a 3x on the outside or whatever. That makes sense? Everybody? Those are the ones we just did. Okay? That's just one of the things you might try. Try. Okay? It does not always work. Okay? And so we need some other options. Now, all of our options are pretty much going to be based on all of those antiderivatives that we already know. Okay? So this is not something raised to a power, and even if you did raise it to a power, the power would be the -1, and you know that's going to be a problem. Okay? So what we're going to do here instead is we're going to let u equal the denominator. Okay? We let u equal the denominator. Well, what's the derivative of x plus 5? 1 or just 1 dx. So dx is equal to du. So I can go here and say the antiderivative of 1/u du. I'd love to put this one, this particular one, where the denominator is pretty simple, into the free response section of the AP. And I love to put this one in there. So what's the antiderivative of this? Natural log of the absolute value of u, which is the natural log of the absolute value of x plus 5. That's going to be a little bit harder to notice when the numerator is not 1. But let's just walk through this and see what happens, and then hopefully you'll sort of see the pattern of it. Okay? Let's let u equal the denominator. And this time du is not dx. Du is 6x. And I like to go in and show this stuff. Dx equals du over 6x. If you don't show that step and you still get it right, that's fine. Not a problem. Same thing is true about this step. If you don't show this step right here, where you plug in the u and you plug in the dx, replace it. If you don't show this and you still get it right, that's fine. Okay? When I don't show it, I sometimes get my multiplier wrong. That's what happens to me. So I always show it, pretty much. Okay, what happens to the x's? They cancel. And hopefully you'll start to see, when you get to this step right here, you'll be able to see whether that's going to happen or not. Okay? And the 2 and the 6 cancel and give me a 1/3. We'll pull it on the outside. And then I have my 1 over u. So it's 1/3 the natural log of the absolute value of u. And also, when they're not very hard, people often skip that step right there and go straight to this one. Okay? And just a little comment on natural log. You know, the natural log function, like this. What's its domain? Yeah, all positive numbers, no negative numbers, right? So if we want to be able to deal with this 1 over u thing, we have to just say absolute value. Sort of picks up this side over here is what it does, as if there's another side over there. But the thing is, when you look at the answer that you get, sometimes they will leave off the absolute value. Okay? So they will leave off the absolute value when you don't need it. When do you not need it? Well, you don't need it if you plug in a positive number in. If I say the natural log of the absolute value of 4, do you need an absolute value? No. So when your argument is always positive, always, then you don't need to keep the absolute value there. All right? This answer is right, but if this were a multiple choice question, it's pretty likely that the answer that they would have would look like this. Because 3x squared plus 4 is never negative. Yes? Okay. It also might look like this. Yes? Oh. And it also might look like this. It's not a particularly hard antiderivative, and they're throwing in a little pre-count to check the multiple choice. Okay? If I ask you for the answer, they're all right. Okay? So this is just a multiple choice thing. Is there a question? Oh yeah, let's see on the line. Thank you.
How is multiplying locals in the sequence?
Now, I'm not going to reteach this, but this is equal to this. Yeah. Okay. All right. So option 2 is if you have the antiderivative of 1 over f of x. It can be messier than that. It can be 2x over f of x, or something messier over f of x, but whatever it is, one of the things is to let u equal the denominator. Let u equal the stuff that's raised to a power, let u equal the stuff in the denominator. Those are 2 things you might try.
And that's what we just did.
That's what we just did. There's always sometimes like a little weirdness that goes on. We're not going to be able to do problems that come from quotient rule and product rule. Even though this answer is a quotient, we don't have to pull the quotient rule for this. Okay. I cannot just take the answer from the top and the antiderivative log. It doesn't work. You get the wrong answer, so don't do that. Okay? So we have to think of something else, or else we have to skip the problem. And the only thing that I know how to do, well, I know this. If this were just a plain x, what could you do? Yeah, you would split it all up, yes? Everybody remember that? Okay, so you can expand that just a little bit. And you can do this. That idea. Go ahead and just divide it. Okay, we've already reviewed this, long division. Synthetic works on this, for those of you who like synthetic. Doesn't always work. Oh, it's 3x minus 16. That's fine. Okay, awesome. Remember the long division? So the original function is equal to this function. same thing. This is also true if you were doing derivatives. If I told you to take the derivative of this thing, you can start by writing it over again. If you like that idea, just copy it usually easier. But for antiderivatives, it's nice. So what I'm going to do here is I'm going to break this up into this nice, easy one that I don't have any problem with, and then I'm going to break it up into this one over here that's going to give me just a tiny little bit of trouble. Okay? Antiderivative of x. 1/2 x squared. Antiderivative of 2. 2x, yes? Minus.
Can you do option 1, please?
No. Because there's not one thing raised to a power.
Option 2, please.
That's what I'm doing on this one. Okay. So option 2 here, I'm going to let u equal x plus 1, but only on this last piece, not for the whole thing. Only on that last piece. So I end up with, and some of these are super easy. When you get du equals dx, that's a nice one. I like to do that. With these simple, these super easy denominators. Just have to keep straight that part of this problem is in x, and part of this problem is in u. And a lot of times people will just skip right back. It's going to be the natural log of the absolute value of u. Just go ahead and pop that back in. And then plus c. Okay? We're good? All right. Option 3. I'm going to stop writing the functions. Let u equal the argument of a trig function. I can figure out a way to write that one, because you can do it for any of the trig functions that you know. So let it equal the argument. I know the antiderivative of the sine of x, but in order to do the antiderivative of the sine of stuff, I need this little u substitution. If you read through what the book says about pattern recognition, and if you work enough of these problems, you don't have to actually show this work that I'm showing. I'm going to keep showing it. It's good for you. Okay? And when a problem is more difficult and you don't see the pattern, this is the way to go. Okay? But for simpler problems, once you see the pattern, that's great. Sine of u. And then dx is du divided by 3. So I end up with just that nice constant multiplier on the outside. Everybody see? All right, so 1/3. The antiderivative of sine, I always have to stop and think about the negative. The derivative of cosine is negative sine. So the antiderivative of sine is negative cosine of u, and then make sure that you plug that in, that original argument. Okay. How's it going? You okay to feel for this? Yes? Okay, I'm going to tell you that you're going to start to see shortcuts, and I'm super happy for you to use shortcuts. But if you're not careful, you'll get your constant multipliers wrong. Like you ended up with a constant multiplier of 1/3 here. People who are not careful end up with a 3 there instead of a 1/3. That's what happens. Okay. So if you want to try the shortcut, try it anytime you want. And if you always get your constant multipliers right, then obviously you've got that gene that allows that to happen. I don't have it. Okay. I have to be really careful with this. So what's the derivative of x over 2? Don't be thinking that hard. Yeah, this is 1/2 x, right? Okay. What's the derivative of x over 2? Lay it on the side. What's the derivative of x over 2? 1/2. Okay. All right. And I love it. It's like in the middle of the test, and then people are doing closer roll, and I'm like, okay. All right. And then the second place people mess up is right here, and they'll tell me that dx is 1/2 du. No, it's not. What is it?
2du.
It's 2du. And this is where what I'm talking about, where I'm saying if you're not careful, you'll get your constant multiplier wrong. Okay? All right, so what is this going to say? The integral of the cosine of u times 2du. And anytime you want to, just start popping that constant multiplier to the outside. Okay? Derivative of sine is cosine. The antiderivative of cosine is sine. And go on to your, yeah, that can always save you a little bit. Okay, well, on most of the problems I have put it here. And then I've shown one more step. But once you're sure you know what your constant multiplier is, you can go ahead and move it to the outside. So you're sure of that. Okay? Yes? Okay, what option am I on? We're going to write a list at the end of all of them together. Option number 4.
Yeah, how many options are there?
I don't know. I'm just okay.
Freak you out.
Let u equal a trig function. I think there's about 6.
From impact, like,
Well, you know, I really get on. I can't read it.
how many
I'm
options?
not gone through all 5 or 6 options.
6 what?
Oh. I totally, I can't, I don't know, I did them earlier, now it's done. Okay, ready? Right up there. Okay, so one other thing to try is just to let u equal an actual trig function. So I'm going to use this problem to state something that you'll hear me say more than one time. Not lots of times, because there's no. It never, ever, ever, ever helps to let u equal x. This is a pointless exercise. If you let u equal x, you didn't change anything, okay? So that's not a choice here. Does that make sense? So our only other choice is to let u equal either this or this. And I'm going to tell you right now that either one of them is going to work. But I like, it doesn't matter which one you pick. You can pick either one. Your answer ends up looking a little bit different, but they're both right. So look what happens on this one. What is the derivative of sine? Nope. Cosine. And look, yeah, the derivative. Okay? So here, you can start to see, here's my u, and here's my du sitting right there. You know what I see? When it's that clear and there's no constant multipliers, I would probably stop right here, not show that next step, and just change it to the integral of u du. This turns out to not actually be a trig antiderivative. It's a power rule. Okay, one more time. Hold on. What did I take? What did I change that to? U. And what did I change both of those to? Du. Y'all see? Oh, that was fun. Okay. This is the, okay. When I talk about pattern recognition, this is what they're talking about. When I show you the way I do it, it looks like this. And then when you write it down, you write this down, and then you cancel it. And what do you still get? U du. Do y'all see? Okay. Oh, I like that. Oh, that was nice. The integral of u du. Okay? So that's, the answer to that is 1/2 u squared plus c. So the actual anti-differentiation doesn't involve trig. Okay? Now, is the answer going to have trig in it? Yes. I'm going to put trig back in. What was u? Sine of x. Sine of x. So the answer is sine squared of x. You can either write that as sine squared, or you can write it as the quantity sine of x squared. Okay? Two more, and then we'll take a little break. But only because you were inside, so very. Was it? Jordan. Okay, cosine squared of x, sine x. Remember, when you see this notation right here, you don't have to write this over, but this is what it's saying. And when you write it in the second way, it's really clear what the internal function is. What's inside another function. And the answer is cosine, so that's what I'm gonna choose. And luckily, the derivative of cosine is negative sine. And can you see from here that this sign is going to cancel that sign out? So what you have to decide is, do you need to keep showing this step? Or not, and that's up to you, okay? Show it as long as you need it. Quit showing it when you don't need it. So this ends up with the integral of u squared. I'm going to have sine of x here and du over negative sine of x. What's that going to leave me with? Yeah, just a negative du. That negative is a constant multiplier, pop it right on the outside. Okay? So again, my anti-differentiation itself is not trig. The trig comes back in, and I try to remember what the heck u was. Cosine. And you can either write it with the parentheses or without the parentheses. Okay. Okay. Actually, I think we will pause for just a minute right here. Watch y'all stand up. Okay. A little break. Now we're back.
Hi, everyone. Hi. Hi, Rachel.
All right.
Oh, Rachel, I missed you.
This is an interesting problem for a couple of reasons. Okay. I did. 11. Okay. So here we go. Makes it very real. This is an interesting problem here. Hopefully you can split your page into two halves here. We're going to work this problem two ways. Okay. I might have to write a little bit smaller. If not, just be prepared to do the second one below it. Okay. So we've got all this trig here, and it never helps to let u equal x, right? So the only other option is to let u equal one of these trig functions. So I'm going to show you two different paths to this. One is to let u equal tangent of x. And why is that going to work? Well, because what's the derivative of tangent? Secant squared. And what is sitting right there in the problem? Secant squared. Y'all see it? Okay. So I'm going to do that shortcut thing again, where I replace this and I replace all of that. Give me the integral of u du. Do I see? And that is 1/2 u squared plus c, which is 1/2 tan squared x plus c. That's easy.
Wait, the dx goes away.
Okay, so I'm skipping sometimes. Sometimes I skip the step. If you don't see it, then you definitely need to keep showing the step. I'm going to solve this for dx, which is du over secant squared. And then I'm going to take out the dx right here and put du over secant squared. And what happens to the secant squares? Okay. So you can show that. Some people can see that step. For me, I can only see it when it's really easy, like when this exact thing is exactly what's sitting up there. But whenever there's an extra constant, I usually show that extra step of work. Okay. So either way that you want to do it. Okay, we got an answer, 1/2 tangent squared. Let's see. Okay. Option number 2, because one of the things I told you to do is set the u equal to something that's raised to a power. Yes? So you might think, well, I need to set this equal to secant because that secant is raised to a power. What happens if you do that? Well, the derivative of secant is secant x tan x dx. And I'm going to, this one's not just sitting there for me, so I'm going to go ahead and show that other method again. Du over secant x tan x. I don't know that this one's quite so obvious, but I think it's interesting that you can do it. Pick it up. You ready? Okay, I'm going to take that that integral and write it over again. Tan x times secant x times secant x. I just copied it over again and I took a square off of it. I'm gonna take one of them, this one, whatever, make that one into the u. Very good. I'm gonna leave the other two up there. I'm gonna take dx and change it into du over secant x tan x, and what happens? What happens to that extra secant x and that extra tan x? It goes away. Now, I'm not so sure that you would have noticed this path. That's okay. Your path is all right. So I end up with the same thing, u du. End up with the exact same thing. Okay? Two different paths. And that answer is 1/2 u squared plus c. But when I substitute in, I don't get 1/2 tan squared. What do I get? I get 1/2 secant squared. And I'm telling you that both of these answers are right. They are not exactly equal. So I'm going to talk to you a little bit about why they're both correct and why they're not exactly equal. But we'll see how that works. Okay, so go to the Pythagorean identity. You remember sine squared plus cosine squared is 1. So I want to get tan squared. So I divide both sides by, what's tan? Sine over cosine. So I'm going to divide both sides by cosine squared. Maybe y'all have them all memorized. I do not. Tan squared plus 1 equals? There, secant squared. Tan squared plus 1 equals secant squared. Y'all see? So what's the only difference in tan squared and secant squared? Which is a constant. Okay? So if you work with this, if you have to work with this and do stuff, you're going to get one constant. But if you work with this and do the same stuff, you're going to get a different constant. But other than that, they're all going to be the same thing. Do y'all see? Okay. Yeah, we have this right. Okay? All right, one more trig one and then, no, two more trig one.
Yeah, and are we still doing it 2 ways?
We did that one 2 ways.
Yeah, but are we?
No, we are not. One time only. Actually, that problem just makes the point that sometimes there is more than one way to get the right answer. Most of the time, there is a shorter, easier way. Most of the time. Okay? So, look at everything that's going on in this problem. Okay? The one thing that's not going to do me any good is to let u equal x. That's not going to do me any good. So, you have to make a choice. What am I going to let u equal? One choice would be to let it equal secant of x.
Are we doing them both ways?
We're just going to look at it, because this is what's really going to happen when you get to one that's difficult. Well, if I let it equal secant, then what's the derivative? Secant tan. And I want you to look and say, see, if you plug u up here, is this part, going to cancel the rest of it? No. Not going to do that. Okay, don't erase it. You need to recognize that sometimes you make a choice and it doesn't necessarily work. You could let u equal tan x. One of the choices, let u equal one of the trig functions. Okay? If you let u equal tan, then what is du? Secant squared. So your real question is this secant squared sitting up there in the problem? Does it look like it might cancel out if I work through this?
Yeah.
You want to go with that one, okay? So it looks like it might. When they get a little complex, even though I sometimes do skipping on the super, super easy ones, when they get a little more complex, I have a tendency to show this extra step of work. Okay, it's up to you. I'm going to change this tangent, square root of tangent is going to become u to the 1/2. Is everybody good with that? And then I take out dx and I pop in du over secant squared. Just whether you can see the exact canceling or not, just depends. Some people can see it, some people can't, some people see it sometimes and not others. Okay? And that doesn't make any difference. But I get it all done, and this whole integral becomes just the integral of 1 over u to the 1/2 du. Yes? Now, if that were 1 over u, the answer would be natural log, but it's not. It's 1 over u to the 1/2. So I'm going to change that to u to the negative 1/2, and now I'm going to use the power rule on it. And I get 2 u to the 1/2 plus c. And finally, resubstitute whatever u was, and was u tangent this time? And whether you put it back as a square root or leave it as 1/2 power, doesn't make any difference, depends on what the answer are at the bottom of the page. Okay? Okay? So what are our two options here? U equals 3x, yes, or sine of 3x or cosine of 3x. Those are our two options. I'm going to tell you both of them will work, okay? I'm going to show you the one where I let u equal sine of 3x. The other one will work. It takes a little bit. You kind of have to substitute twice. You do it once and then you have to do it again, okay? And you should see that in here because this is double chain rule, okay? Because you've got sine times cosine, and you've also got sine of 3x. It's a double composite function here. So what's going to happen when I take the u? I'm going to get cosine of 3x times 3, which a lot of us are pulling that forward, yes? And then on the outside I'll put a dx. Can you see how this is going to lay out when I substitute from here? Then you may do it. Okay, I'm going to go ahead and finish the long play, showing the extra step. And I end up with the integral of u. The u, lost something. Lost 3. That constant multiplier is the thing that gets lost most often. So where does that belong in my answer here? Outside. 1/3. Okay? So I get 1/3 times 1/2 u squared plus c. And my final answer is 1/6 of the sine squared of 3x. You see all of that messy chain we're going on. If you were to take this derivative, these are the ones that we had some trouble with. Yeah. Okay, so how many options have we had? We had function to a power. Yeah. We did stuff to the n, like u equal to stuff, yes? We did 1 over stuff. U equal to stuff. Inside the power, in the denominator. What else do we have? Say it again? U equal to argument of trig, or let u equal a trig function. When you get to trig, you gotta kind of, may have to try more than one thing. Sometimes you pick something that doesn't work. So we're just gonna pop this fifth one right here because this is like the easiest thing on the planet. If you have an integral that involves e, what's the integral of e to the x? E to the x. So if we have e to something else, we're going to let u equal that something else. You want to put stuff here instead of f of x, and put an x with all the other things. Let u equal the stuff. And that's true for that a one as well. Okay? For that a, and also a stuff. Okay? I think that's my last one. I'll do a couple of these. Okay? Can't read my handwriting. I think I'm on number 14. If I had an extra 3 weeks, I would give you a day where I gave you nothing but the easy ones. The ones where you could practically just see it without writing anything down. Okay? But we don't have time for that, so I'm gonna let u equal the exponent and du equals 2dx. Okay? And here's the place where some of y'all can see what's x going to end up as. Is that gonna end up as a 2 in my final answer or as a 1/2? It's gonna be 1/2. And some of you are like, I didn't know that. Okay, if you're one of the people that says, how do you know that? Then do this. And then you don't have to guess, okay? Change it to dx. All right, so I'm gonna end up with the integral of e to the u, and this is gonna be du over 2, so I get a 1/2 on the outside. Okay? Pop it right back in. 1/2 e to the u plus c. 1/2 e to the 2x plus c. Okay? Okay. Okay. This is quite a bit more complicated than what we're used to dealing with, except for the ones where we had calculators. This is quite a bit more complicated. You've got choices to make here. Do you want to let u equal the denominator, or do you want to let u equal the exponent on the e? Given that we're working with exponents on the e, let's go with that one. But sometimes you're going to pick one and it's not going to be the right one. Okay? All right, so du is, make sure you're doing the derivative, not integral. Okay? -1 x to the -2 dx. Now, raise your hand if you can see how this is going to lay out with that when you first just glance at it. Some of you can? Yeah, not me. Okay, I just can't. So I'm going to mess with this. First of all, I hate negative exponents. They're very useful, but when I need to really figure something out, I don't like them. Okay? And if I need to solve for dx, where is that x squared going to end up? In the numerator, like this. Not in the denominator. Which is a good thing, because where is it in the original problem? In the denominator. So it needed to end up in the numerator so it would cancel out. Does that make sense? Okay, first I flipped it from here to here. I just flipped it. Now let me make that. Okay. All right, back up to my problem. I've got the integral of e to the u over x squared times negative x squared du, or negative integral e to the u du. What's the integral of e to the x? E to the x. What's the integral of e to the u? E to the u. I'm going to go back and substitute in whatever u was. And there we go. All right, those are our choices here. Let me let u equal denominator, okay? You could try letting u equal e to the x. That has in fact worked. Did everybody hear that suggestion? That has worked in some other situations, okay? But in this case, I think we're going to go with the denominator. So even though this problem has e to the x in it, we're choosing one of our other options, okay? So what is the derivative of 1 plus e to the x? the x, and aren't we lucky? Because what's floating up there that's gonna be in the way? The need of the x, okay? I'm gonna just keep working, I'm not gonna talk. Until I work at your own pace. Well, that's not talking means it's gonna work for me. I try, but I fail. And I end up with the interval of 1 over u du. Yes? Okay? And what is that? The ln. So our answer here is the natural log of the absolute value of u. Anytime you let the denominator, the whole denominator equal u, this is what you're headed towards. Okay? And then resubstitute in at the very end, the natural log of the absolute value of 1 plus b dx plus c. And then I want you to think, do you need the absolute value on this or not? Think, don't answer, think.
Yes.
What does e to the x look like? Always positive. Now add 1 to it. It is always positive. So if it's always positive, do you have to have the absolute values on it? Is it wrong to have them, but you don't need them anymore? Okay?
Why aren't you looking at X signs?
Okay. I'm looking at this. So what I'm here, whatever x is, doesn't matter what x is, e to the x is always positive. Take e and raise it to any power you want. It will always be positive. Add 1 to it. Always positive.
Because either the -1 would be a positive value to the y.
Okay, so e to the -1 equals 1 over e, which is a positive number. Yes? Yes? Okay, good. 2 problems to go, I think. Okay? I'm going to put numbering. Now, when I create this worksheet for you guys, out of the problems from 5.5 and 5.7, I'm probably going to just do a handful that are indefinite intervals, and then I'm going to jump to definite intervals. Because in order to do definite intervals, you have to be able to do indefinite intervals, okay? And this just kind of cuts the total number of problems down. All right? So looking at this, thinking back over all of our options, what do we want to let you equal? Very good. The internal, something internal raised to a power. Hopefully our du will contain an x, and it does. Du is 2x dx. All right. Now, I'm going to put my indefinite interval here, and I'm going to get a 1/2, and then u cubed du. Agreed? Okay, so here's the difference when we get to definite intervals. Are y'all all here with me? Okay. When I take this antiderivative, what variable is it in? U. What variable is that? That's an x, that -2. So there are 2 ways you can do this. You can take the antiderivative, change it back to x, and plug in the number. But the easier, almost always quicker way is to take this number right here and change it into a u value. How do you do that? Well, right there. What does u equal? X squared plus 1. So if x is -2, then what's u?
5.
5. It's not even negative anymore. Okay? At the same time, you need to go up here and do this one. Change it into a u value. U squared plus x squared plus 1. So 3 squared plus 1 is 10. Not -10. Okay? All right, so we're going to do our antiderivative. 1/2 times something, 1/4. U to the 4th. And we're going to evaluate it not from -2 to 3, but from 5 to 10. Notice I don't have a plus c anymore. Yes? No more plus c. So I'm gonna give the 1/8, and I'm gonna say 10 to the 4th minus 10 to the 5th, and then I'm gonna quit because, really, who cares? Okay? Good enough. I mean, I did that on my last year's notes too. It's 5 to the 4th. Thank y'all for catching that. Like in my notes, it says 10 to the 5th right there. I'm like, what's wrong? It's 5 to the 4th. And if you had to go any further than that, you really need a calculator. I mean, you could do it if somebody offered you $1 million, but short of that, pretty much not worth it. Okay. Okay. Ready? What are we gonna let U equal? The denominator. So we're headed towards an LN. Yes, when we let U equal the denominator, we're headed towards an LN as our answer. Okay? So du is just 2dx. I'm going to end up with the integral of 1 over u du, 1 over 2, 1 over u du, and I'm going to have what constant multiplier? 1/2. And then you've got to change this x value into a u value. When you do it, with this. 2 times 1 plus 1 is 3. And then you change the top one into a u value. 3 times 2 is 6 plus 1 is 7. Okay? All right, so we get 1/2 times the natural log of the absolute value of u, evaluated from 3 to 7. In this case, am I going to need the absolute values? Just because I'm plugging in positive numbers. Okay? So we get 1/2 times the natural log of 7 minus the natural log of 3. All right, cookie. We'll give it to someone who can tell me what you might do with that. Eat it, the cookie? Ellen of 7/3. Chrissy gets the cookie. She may not have been the first person, but she's the loudest. Which is hardly ever true. So there you go. Ellen of 7/3. Okay? That's a fair chance that it would be that. What else might they do? Probably not. They might. 7/3 to the 1/2 or square root of 7/3. Yes? I like that first one. Just fine. Okay? So how many cards I told you have? That one was last one. But these last few problems are about definite integrals, yes, but they're also about, okay, we've got all these options, which one do I pick? I got multiplication going on here, I got powers going on here, I've got an e in there. What do you think is going to, when you set this one part equal to u, that its derivative, or a part of its derivative, is floating around in the problem as well?
Is this x cubed?
That's x cubed over 2, which is the same thing as 1/2 x cubed, right? Y'all okay with that? You like that better? 1/2 x cubed, that's that exponent. Okay? That's this right here. So du is 3/2 x squared. I know I'm going to mess this coefficient up, this constant multiplier up, but I don't actually solve for it. You might not. You're better women than I am, bless you. So I'm going to multiply by 2, yes? And divide by the 3 and divide by the x squared, yes? So I'm going to have 2 over 3x squared du, or 2 du if you like it better like that. Okay? All right, so the antiderivative, I have an x squared, I have an e to the u, I have a 2 over 3x squared du. If you put this step in here, several of you doing, if you put this step in, this, a combination of X's and U's, then you have to tell me what these numbers are. Okay? You have to put a variable there. Either you're leaving it as X or you're changing it to U. If you go straight to the U, then you don't have to do that. But I'm gonna go ahead and change it because it's almost always easier. So -2 cubed is? -8 divided by 2 is? -4. And 0 cubed is? Divided by 2 is? 0. And then when you switch it to this, is that a 2/3? When you switch it to this, unless you say otherwise, it is assumed that those are U's, because that's what the problem is in, okay? So it turned into a nice, easy antiderivative, e to the U, and I'm going to just plug into that -4 and 0. Okay? Very good? Okay, one last little thing right here. Okay? This answer might be a multiple choice answer, but almost certainly not, because what's e to the 0? 1. And almost certainly, okay, we change that into 1/e to the 4th. Yes? And then there's a pretty fair chance that they would combine this so that it has a common denominator, like this. Yes? Pretty fair chance, which would give you what? -1. Okay, that's probably about it. I might pop that 2 in there, that's pretty good, probably not. Or it might be a decimal. Okay? Very good? Okay.